This lecture is about interrupts and exceptions. We will discuss in detail how interrupts or exceptions are occurred and how they are handled. So we'll have two parts. One will be the hardware part and the other one will be the software part. The hardware part will include interrupts and exceptions, interrupt or exception handling, interrupt request lines, programmable interrupt controller, while the software part will include nested execution, kernel stacks, and the explanation or discussion of the work queues and threaded interrupts. So this is a simplified architecture diagram. The central processing unit and the main memory is connected with the I/O devices through a system bus. There is a common system bus which includes all the data buses, address buses, and control buses. So the utility of a general purpose computer, it mainly depends on its ability to interact with the I/O devices. These I/O devices may be keyboard, display, disk driver, network, or other related devices. So all the devices require a prompt response from the CPU when any kind of external event occurs, even when the CPU is busy while running a program. So mechanism for a device to gain CPU's attention is needed during the program execution. So interrupts provide a way doing this. How it is done, we will discuss in detail during our interrupt handling process. So this figure presents instruction fetch or execution cycle. We have discussed in detail the instruction fetch and execution process in our previous lectures. So the instruction is being fetched, decoded, and executed, and the next instruction is being pointed with the help of program counter. So what if any interrupt, internal or external interrupt occurs? So if there is an interrupt which is occurred during the program execution, so the interrupt will be saved, the context of the interrupt will be saved, interrupt ID will be obtained, it will be looked up in the table, and then the interrupt will be handled. So if there is no interrupt, the system normal routine or normal execution of the program will be continued. So what are interrupts? The forcibly change of the one normal flow of control sequence, it's known as interrupt. It is similar to context switch, where hardware saves some context on the stacks, which include interrupted instructions, and also enter kernel at a specific point, which figures out which interrupt handle should be used, and the normal instruction execution will be resumed with special I return instruction. So it will be discussed in detail in the next slides. So we have different types of interrupts. These are asynchronous and synchronous interrupts. The asynchronous interrupts are from the external sources, which may be the IO devices. It has no relation to the instruction which is being executed. The synchronous interrupts, they are also called exceptions. These are the processor detected exceptions, which includes faults, traps, and aborts, while the program exceptions are related to the request for kernel intervention. it are with the software instruction interruption or the system calls. So what are the faults, traps and aborts? Uh, the faults, traps and aborts occur during the instruction fetch or execution process. So the fault occurs for that instructions which are illegal to be executed. For example, we want to write a memory segment which are for only read only purpose, or we want to read from an unavailable memory, a memory which is not included or listed in the memory. We want to read from that typical or particular memory location, or if an executing or execution of a privileged instruction, a instruction which is not included in a instruction set, system want to execute that particular instruction. So different scenarios or cases where faults can be occurred. So the faults are detected before incrementing the instruction pointer. The causes of faults can also often be fixed. If a problem can be remedied, then the CPU can just resume its normal execution cycle. So traps occurs when a CPU that might have been programmed to automatically switch control to a debugger program after it has executed an instruction. So that type of situation is known as trap, and it is activated after incrementing the instruction pointer. So one occurs during the instruction fetch process and the other occurs during the instruction execution process. So we have different error exceptions. Most error exceptions include divided by zero or an invalid operation or an illegal memory reference. These are all the exception types. This isn't a coincidence. The kernel job is fairly simple, which sends the appropriate signal to the current process. That will probably kill the process, but that's not the concern of the exception handler. So one of the most important exception is the page fault. So different type of exceptions can be occurred during program execution. Internally, they might be related to the memory location, invalid instruction, invalid operation, and any other processes or instruction types that may occur for the exceptions. So there are total 256 possible interrupt ID numbers. The Intel reserves the first 32 for exceptions, and the operating systems such as Linux are free to use the remaining 224 available interrupts. That may depend on the purpose, which are for service requests, for other purpose system, which include system calls. So we have some examples of the interrupt ID numbers. 0 is for divide and overflow. A 6 is defined for undefined opcode. 7 is used for coprocessor not available. So different ID numbers, they represent different type of interrupts or exceptions. So how these interrupt will be handled by the hardware? We have two programmable interrupt controllers. One is the slave and the other is the master. The slave accepts different signals from different IO devices, and then it passes the signal to the master program interrupt controller. So if there any interrupt occurs, the slave will transfer this interrupt to the master, and the master will then transfer this interrupt to the CPU, where the interrupt will be handled. First, its ID will be matched, then it will be handled depending upon the nature of the interrupt. So, what the interrupt controller is responsible? It is responsible for telling the CPU when a specified external device wishes to interrupt. It needed to tell the CPU which one among several devices is the one that needed the services. So program interrupt controller translate interrupt request to vector, which raises interrupt to the CPU. It informs the CPU about the interrupt. Then the interrupt will be matched with the interrupt number, ID number, and the acknowledgement from the CPU will be then processed back to the program interrupt controller. So interrupt can have different priorities. There may be low priority or there might be high priority for the interrupts. So the interrupt which have low priority, they will be handled after the instruction execution process, and the interrupt which have high priority, they will be handled during the instruction process, fetch or execution process. So depending upon the type of interrupt, a high interrupt will be handled first, and a low priority interrupt will be handled after the execution cycle. So here we have example of an interrupt on 8386 processor. So if there is one interrupt line and one interrupt acknowledge line, so the interrupt controller raises INT line, or it gives a high signal to the INT control signal. The core pulses INTA line, it lows allowing the interrupt to go low, and then there is a signal controller to put interrupt number on the data bus. So we have three processes. One is for the interrupt controller, the other is for interrupt acknowledgement, and the third one is about the interrupt number. So during multi-core CPU processors, when there are multiple interrupts, they are occurred, so they are handled by local or advanced program interrupt controller. So these all program interrupt controllers are connected with the system bus, and the interrupt handling phenomena is occurred or dealt by the multi-core CPUs. So here we have different program interrupt controller types. We have advanced program interrupt controller, which is used in all modern systems. We have a local A program interrupt controller, which is also known as LAPIC, local advanced program interrupt controller. And we have also a IO EPIC, input output advanced program interrupt controller. So all of these program interrupt controllers are used for interrupt handling. They give different interrupt signals to the CPU, and depending upon the nature of the interrupts are handled. So during the interrupt routing, the broadcasting is allowed, or selective routing of the interrupts is being done. The ability to distribute interrupt handling, or the load of the interrupt, is being distributed among different interrupt lines, and it routes to lowest priority process. So it is done with the help of different special registers, which are task priority registers. So they are responsible to deal, or they are responsible to handle the interrupts depending upon the nature or priority of the interrupts. So when there is any interrupt, either in internal or external, these are given to the program interrupt controller. Program interrupt controller signals the CPU, and CPU, it then gives the interrupt descriptive table to handle this interrupt for its nature or depending upon its nature. So interrupt requests are assigned to the devices which are the hardware dependent. Sometimes it's hardwired, sometimes it's set physically, and sometimes it's programmable. So it usually assign interrupt request to the at the boot time, and some interrupt requests are fixed by the architecture. So interrupt request 0, 1, 2, and so on. These are different for different processes. It may be for interval timer or cascade pin. So different hardwired or programmable interrupt requests are done during this process. So during the assigning process, we have discussed that there are total 256 ID numbers for the interrupts. So these 256 interrupts are defined in the interrupt descriptive table. So among these 256 interrupt ID numbers, below 32 are reserved for non-maskable interrupts and exceptions, and the maskable interrupts, these are assigned depending upon the nature or the need of the interrupts. For example, vector 128 is used for system call, or vectors 251 to 255 are used for the IPs. So the interrupt descriptive table will be responsible for the entry point where it gets the descriptors, where the segment selectors, offset for handler, descriptive privilege level, and gate process is done. It will be responsible. The gate will be responsible for different uh, tasks or processes, which includes the transfer of the interrupt, or disabling the further interrupts, or enabling the further interrupts. So the interrupt masking is done in two different types. One is global and the other is selective. The global masking is done where all the interrupts are delayed, and the selective interrupt masking is responsible to individual handle all the interrupt requests. See how the interrupts are dispatched. Each interrupt has to be handled by a specific or special device, depending upon the interrupt descriptive table, where all the interrupts are given the specific ID number. So the hardware locates the proper gate descriptor for this interrupt vector and locates the new contacts. So a new stack pointer, a program counter, CPU and memory state, they will be loaded, and the global interrupt mask set the old program counter, stack pointer, memory, CPU, where we are saving uh, the description or the detail of the instruction or the interrupt. So if there is interrupt which is occurring, if the interrupt priority is high, so the instruction or instruction process cycle will be halt or it will be paused. The information will be stored to a temporary location which may be a stack location. When the interrupt is handled, uh, that particular instruction information will be then transferred to the memory from the stack. So up to now we have discussed when there is a single interrupt which is occurred during instruction cycle. What if there is a nested interrupt which is occurred? It's also known as interrupt within the interrupt. So it also will be handled according to the priority level. If the interrupt level, if the interrupt priority level is high, the interrupt will be handled first, and if the interrupt priority is low, it will be then handled uh, after the instruction execution cycle. So nested interrupts or exceptions can be occurred. Different interrupts can also be interrupted, and there may be exceptions within the exceptions. So we have different interrupt handling philosophy. We have also discussed earlier that the interrupt handling process will be occurred on the basis of interrupt priority. So if the interrupt priority is high, then the interrupt will be handled first, and if the interrupt priority is low, the interrupt will be handled at the end or after the instruction fetch execution cycle. So it is linked with the top half and the bottom half. So the top half will be responsible for the high interrupts. So all the execution, all the processing of the interrupt will be handled uh, firstly, and it is also known as it is also referred as do it now. So technically, it is the interrupt handling process where the interrupt will be handled first. Uh, the whole process will be same. The CPU will send the request to the interrupt descriptive table where the interrupt ID number will be matched. The interrupt ID number will look up for the interrupt number, and then it will execute or it will handle the interrupt depending upon its nature. So the second philosophy for interrupt handling is bottom half, which is also referred to do it later, and they are linked with the low priority level of the interrupts. There are different mechanisms to defer work to later, which are linked to the soft task legs, work use, kernel threads. These are related to the OS categories. So here we are only focus on the interrupt handling process. So if we have two interrupt handling process, one is the top half and the other one is bottom half. So in this lecture we have discussed different interrupt types, how these interrupts are occurred, and how these interrupts are handled depending upon their priorities.